And lastly, let's just see how to use matrix multiplication in Python. We're just going to add a few little things to our toolbox here. And here they are. The a dot dot method is exactly the same thing we used for matrix vector multiplication, and that's what we're going to use here to multiply two matrices together. Easy as pie. Again, you can use the splat operator to say a times b, but that's just going to multiply element by element and will only work if the matrices are exactly the same size and shape. Occasionally that's useful, but when we talk about multiplication in the linear algebra sense, we mean this thing here that you get with the dot dot, which is what we've been doing this entire episode. All right? Taking the inverse of a matrix is linalg.inv, and you will give it a matrix here that you want it to take the inverse of. Remember that you are going to get an error if you try to take the inverse of a singular matrix, and we'll see what that error looks like in a minute or two. Finally, if you are solving a system of simultaneous equations, like the ones we've been doing in the last couple episodes, you can, of course, take the inverse of the matrix A and then multiply it by B here. I don't know why they use B typically as the letter for the right-hand side of these equations, but for whatever reason they use that. But anyway, if I have equations that I've set up in this format, I can just take the inverse of A and multiply it by B. It turns out, though, that it's faster and it's more numerically accurate. You're going to get less of a round-off error if instead of using the inverse method there, you let Python do its thing with the solve function. And what it's going to do is use this technique called Gauss-Jordan elimination, which we're not going to learn in this class. But basically, it's a way of solving simultaneous equations very quickly with very, very little round-off error. And so you should use that instead of the inverse. The reason I'm teaching the inverse is because the inverse is used for a lot of other things besides just solving sets of simultaneous equations, and because it's very, very important theoretically to understand what the inverse of a matrix is and what it represents. All right, so let's get started. All right, so let's go to Spider here and just add a few matrices here in the console. First, we have to import numpy. And let's make a matrix called A. We'll make it a 2 by 2 and just throw some kind of random junk in here just for illustrative purposes. And we'll make a matrix B of the same size. And, oops, forgot a box there. And then let's make a little bit bigger one. I'm going to make one that has, how about 2 by 5 rather. There. Okay. So I've got A, and I've got B, and I've got C. So first let's do A times B just to show the difference here, right? So if I do A times B, I do in fact get an answer, but that is only the element by element answer here, right? So A's upper left entry was 3, B's upper left entry was 1, it just multiplied 3 by 1 to give us 3, it multiplied 5 by 4 to give us 20, etc., right? Again, sometimes that's useful when you're writing programs, but by far the more common thing and interesting and useful thing to do is this. And that actually gives us the matrix multiplication of the two matrices, right? So you can verify for yourself that if I take the 3, 5 row and I dot it with the 1, -5 column, I do in fact get -22, 37. You can work that out and convince yourself. And as we mentioned before, if I say B dot A, I certainly do not get the same answer. Matrix multiplication is not commutative. In fact, many times it's not even defined both ways, right? So if I say A dot C, then I'm going to get a 2 by 5. But if I say C dot A, I'm going to get nothing, right? And this is the nerd speak for, sorry, you can't multiply those two matrices together because they're not the right size, right? I could certainly take the transpose of C and then multiply it by A. And then I will get back a 5 by 2 because C dot transpose gives me a 5 by 2, which can be multiplied by a 2 by 2. Let's check associativity next. So if I take A dot B dot C, I get back that thing. And that is A dot B, which is that thing, multiplied by C, which is that thing. And so I'm getting a 2 by 2 times a 2 by 5 there, right? Now the question at hand is, what if I did the B dot C first and got that, and then multiplied A dot that thing on the left, And when I do that, yea, verily, I get this same matrix up here. You can see that that is the same matrix as this one down here, even though up here I said A dot B and then dot C, whereas down here I said A dot and did the B dot C first before I dotted it with A. Okay, so that means that the two matrices are associative, which means that I can multiply them in any order. It doesn't mean that I can swap which is first and which is last. It doesn't mean I can swap which is left and which is right. It means that if I have a bunch of operations in a row, I can perform those operations, the right one first, then the left, then the middle one. As long as I don't change the order of the operands, I can perform the multiplications in any order. Okay, let's do a thing with inner product and outer product here. So let me make a D. And I'm going to make this thing be a real long vector, 5, 7, 1, 3, 3, 3, 3, 4. That's long enough. And then I'm going to make another one called E. And this one I'm going to make a tall one. So I'm going to say 4, negative 2, 4, negative 3, negative 1, 8, 9. So how big did I make that? 1, 2, 3, 4, 5, 6, 7 entries. And D has 1, 2, 3, 4, 5, 6, 7, 8. Oh, oops, I wanted to make one more. So let's go back and add this here. We'll make another entry, which will be negative 5. All right, so now E is that guy. So if I do D dot E, that is the inner product, right? And what I get back is a single number. Now, in NumPy speak, this is still a matrix. It's considering it a matrix with one entry, right? So that's just kind of a consequence of doing a matrix operation. You get a matrix back. But it is only one thing long, right? And that's because I took a real long row vector and I dotted it with a really tall column vector. If I had done the opposite, I would get something entirely different, as you see. Now I get every single combination of an element from D times an element from E. And that gives me sort of a multiplication table, as it were, right? In fact, I can make a multiplication table if I had made my things like this. Let's say we had, 1, 2, 3, 4, 5, and then we said E was 1, 2, 3, 4, 5, and now I said D dot E. I get that guy, which is just one number. But if I said E dot D, I get a multiplication table, right? So if I want to know what is 4 times 3, and what is 5 times 4, and what is 4 times 5, I could look it all up in this table, right? Not that's what we use this for, but just to illustrate what the outer product does, which is what that is, right? Okay, last thing, let's talk about our simultaneous equations here. So remember we had an example where we had 6x plus 2y minus 4z equals negative 4. And we had x plus y plus 2z equals 8. And we had 2x minus 2y plus 8z equals 4. And we said that one way to solve this thing would be to cast it as an ax equals b, where the A is this matrix here of all the coefficients. And remember, if I have any missing ones, I have to be careful to put a 0 in the appropriate place. And then B is going to be this in vector form, negative 4, 8, 4. And then it allows me to solve it, right, by multiplying each side by A inverse. Oops. I'm going to put that right there, A inverse. And then I end up getting x equals the right answer, right? So let's see if that works. We're going to make our A, and we're going to say that equal to an array 6, 2, negative 4 for the first row, and 1, 1, 2 for the second row, and 2, negative 2, 8 for the third row. And then let's make our B, which is going to be a column vector of negative 4, 8, 4. And so if I say lin alg dot inv A, I get the inverse of A, right? And again, I don't expect you to be able to look at this A and then look at this A inverse and see how we got one from the other. Again, to me, that's a mechanical, computational issue that the computer takes care of for us. But what's important to understand is what an inverse is, and it's important to understand that if I take A and I matrix multiply by the inverse of A, I get back, I get back this, which is the identity matrix, right? Now, you may be saying, whoa, this doesn't look like any identity matrix I've ever seen. I mean, look at all this 5.5511 stuff. Okay, here's what you got to understand. This is using scientific notation here. And so the upper left entry is 1 times 10 to the 0, which means 1. This is 0 times 10 to the 0, which means 0. This here is 5.55 times 10 to the negative 17, right? So that's essentially 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 zeros. 5, 5, 1, 1, 1, 5, 1, 2, okay? That's pretty darn close to 0, I think you'd agree. So one thing we could do once we have this thing is, we could round it. And if we did that, to a certain number of decimal places or whatever, we could see that it clearly is the identity matrix exactly, right? But it's the identity matrix either way. We just have a little bit of a round-off error. And that's why there's sort of a better way to do it is to use that solve function. But anyway, let's make sure it works this way. So once we have our linear algebra dot inverse A thing, if we take dot B, we get back -1, 5, 2. And if you recall, that was, in fact, the one and only solution to these three equations. If I say x equals -1, y equals 5, z equals 2, plug it all in, that turns out to be satisfying all three of those equations. And in fact, it's the only numbers that do so. And just to show that if we, instead of doing inv, we said, let's solve and give it A and B together, we get back the same answer. And it just turns out that if you have a really, really large matrix, it's 1,000,000 by 1,000,000 entries instead of 3 by 3, it turns out to be faster to use Gauss-Jordan elimination, and it also turns out to have less round-off error. Okay. Last thing, let's just see what happens if we try to take the inverse of a singular matrix, right? So if I went back up to my A thing, where I define that here, I'm going to change the last row to be 7, 3, -2. Okay, oops, left off a boxy here. There. Now you might ask why I set that last one to be those entries. Well, if you see what I did, I added the first row to the second row to get the third row, okay? So now we have a singular matrix because you can get one of these rows out of the other two. And remember, that's the same as being able to get one of the columns out of the other two. And so now if I say lin alg inv A, it comes back and it gives me this humongous answer. And you can tell this is wrong because all of these answers are 10 to the 15th, right? So this one here, the upper left entry is really 3940000000000. And clearly that is not the inverse of A. And what it's trying to do is it's sort of trying to get the matrix that is approximately the inverse. And in order to do that, it's having to set all of its entries really, really, really high. It's sort of like I said, what if I told you to find the inverse, not of 5, which would be 1/5, but what if I told you to find the reciprocal or the inverse of 0.00000000001? The only way to do that would be to get some really, 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 really huge number, right? And so you sort of have to do a sanity check when you're doing an inverse and make sure that the number you get back actually is commensurate with the number that you gave in. Otherwise, you're going to end up with a nonsensical answer. All right? That's matrix multiplication in a nutshell. Take care, and I will catch you next time on All the Math.